Final year students of mechanical engineering from Vigo Institute of Technology and myself Saurabh Adinath Ahire and my colleagues
Ravindra Chavan.
we are going to present the topic on Flyball Governor, which is from Machine Design 2.
The function of a governor is to maintain the speed of an engine within specified limits whenever there is a variation of a load. The objective of our investigation to identify the stress concentration areas and areas which are most susceptible to failure when a governor is rotating about its axis. Also, the value of these stresses is measured. The displacement of various elements of the spindle from the base is also calculated, and the effect on the weights of the arms is a major area of concern for our study, and all the calculations are done considering the weight of the arms. Scottish engineer James Watt introduced the rotative steam engine for driving factory machinery that a constant operating speed became necessary. Between the years 1775 and 1800, Watts, in partnership with industrialist Matthew Boulton, produced some 500 rotative beam engines. At the heart of these engines was Watt's self-designed conical pendulum governor, a set of revolving steel balls attached to a vertical spindle by link arms, where the controlling force consists of a weight of the balls. A flyweight mechanism driven by the engine is linked to a throttle and works against a spring in a fashion similar to that of the pneumatic governor, resulting in essentially identical operation. A flyball governor is more complex to design and produce than a pneumatic governor. However, a centrifugal design is more sensitive to speed changes and hence it better suited to engines that experience large fluctuation in loading. Now we will see the components of the centrifugal flyball governor. Components are sliding collar, bearing, spindle, links, bolts and flyball masses. This is a working diagram of centrifugal governor. Working of centrifugal flyball governor. Power is supplied to a governor from the engine's output shaft by a belt or a chain connected to the lower belt wheel. Governor is connected to a throttle valve that regulates the flow of working fluid, supplying the prime mover. As the speed of the prime mover increases, the central spindle of the governor rotates at a faster rate and the kinetic energy of balls increases. This allows the two masses on the lever arms to move outward and upward against gravity. If the motion goes far enough, this motion causes the lever arms to pull down on the thrust bearing, which moves a beam linkage, which reduces the aperture of a throttle valve. The rate of working fluid entering the cylinder is just reduced and the speed of the prime mover is controlled, preventing the overspeeding. This is a pictorial view of centrifugal flyball governor. This is a model view and this is a SolidWorks model.
Now, as you have looked upon the SolidWorks model of a flyball governor, now let's move on towards its design and calculations. The design and calculations contains the design process that considers the assumptions made in the flyball governor. Now let's design the criteria of the governor. It contains all the legs move exactly like one another. Its total axial deflection at 6000 radian per second cannot exceed 2.3 millimeters. Neglecting the in-plane load effects, the fundamental natural frequency to be below 2000 Hz. 0 is less than or equal to L1 is less than or equal to 2 into L2, and L1 and L2 must be reasonable and comparable. The width and thickness of all sections of the legs are constant. The thickness and width of each leg can vary in increments of 0.25 mm. The thickness is relatively small The height of the short sections of the legs is 4 millimeter. All edges of the legs, except the ones that connect to the shaft, are straight. Now let's look at the design of centrifugal governor. Here AB length of the arm in centimeters, BC is equal to R radius of rotation in centimeters, AC is equal to height of the governor. 30 degrees is equal to alpha is the angle of inclination. Length AB is equal to 41 centimeter, BC is equal to 146 millimeter, alpha is equal to 30 degree. Height of governor WKT H1 is equal to AB into cos alpha is equal to 14.6 into cos 30 degrees, that equals to 12.64 centimeter or 0.126 meter. But h1 is equal to 895 upon n1 square, and n1 square is 895 upon 0.126. The minimum speed required n1 is equal to 84.2 rpm. Assume sleeve lift is equal to 20 millimeter. h2 is equal to h1 minus 20 millimeter is equal to 106.4 mm or 1.1064 m max speed. N2 square is equal to 895 upon h2, that equals to 895 upon 0.335 n2 is equal to 91.46 rpm. The speed range percent, that equals to n1 is equal to n2 upon n2 is equal to 91.77 minus 84.22 upon 84.22, that equals to 8.37%. Let's move on towards the design of spindle. The diameter of the spindle required is d is equal to 13 mm for d less than 20 mm. The torque is equal to sigma y upon 2, where sigma y is the yield stress in Newton per mm square. Sigma y is equal to 380 Newton per mm square. Tau is equal to 190 in Newton per mm square, where tau is the shear stress in Newton per mm square. The WKTT is equal to pi by 16 into tau d cube, where t torque is the shaft in Newton mm is equal to pi by 16 into 190 upon 13 cube is equal to 81962.18 Newton mm, that equals to 81.962 Newton meter. The power required is equal to 2 pi nt upon 60. The max speed n is equal to 91.77 rpm is equal to 2 into n pi into 91.77 into 81.962 upon 60 is equal to 454.94 watt. The power obtained is less than that of the power rating of a FHP motor, which is 746 watts, and hence the design is safe for 13 millimeter diameter spindle. Let's move on towards the design of bearing. The radial force acting on the governor is given by F is equal to torque upon distance. The N force is equal to 81.962 upon 36. The radial force will be 216.75 Newton. For F is equal to 216.75 Newton and the inner diameter is equal to 12 mm. The bearing to be chosen is SKF 6006, SKF 6206 and SKF 6306, out of which SKF 6206 is highly recommended and chosen by us. Let's have a look at the design of a sliding collar. The dimension of sliding collar are as follows. Area A is equal to 100 millimeter square. Force F is equal to 3600 Newton. Sigma is equal to F upon A is equal to 3600 by 100 is equal to 36 Newton per millimeter square. Calculating the yield stress. Selecting the material for sliding collar as bronze, sigma yt is equal to material selected for sliding collar upon factor of safety is equal to 270 by 3 is equal to 90 Newton per millimeter. Sigma is less than sigma yt, therefore the design of the sliding collar is safe. Let's have a look at the design of links. The dimensions of links of a flyball governor are as follows. The area of links would be 100 millimeter square. Force would be 2500 Newton. Sigma is equal to F upon A is equal to 2500 by 100 is equal to 25 Newton per mm square. Calculating the yield stress, sigma yt is equal to material selected for the links upon factor of safety is equal to 60 by 2 is equal to 30 Newton per millimeter. Sigma is less than sigma yt, therefore the design of the links is safe. Let's have a look at the design of the bolts. When the bolt is subjected to the tensile load PT is equal to sigma T upon area is equal to 90 into 7 by 175 is equal to 36 Newton. Materials should be selected for the bolts as stainless alloys. Sigma yt is equal to material selected for bolts upon safe factor of safety 270 by 3, that equals to 90 Newton per millimeter square. Therefore, the design is safe. Let's have a look at the advantages of a flyball governor. The operation of a centrifugal or flyball governor depends on the change in the speed and centrifugal force on the governor balls. Only centrifugal force is in controlling action. The sensitiveness is less when compared to inertia governor. Easy to balance the revolving parts. This type of governor is more frequently used and they are inexpensive. Let's look at it disadvantages. They have large dead bands since the speed measuring device must also furnish the force to move the engine fuel control. The power is relatively small unless they are excessively large. They have an unavoidable speed drop and therefore cannot truly provide constant speed when this is needed. Let's look at its applications. In automobiles, centrifugal flyball governor controls the speed and keeps the speed within the pre-desired speed by operating the throttle valve. Its application also involves in speed control of turbine shaft in hydroelectric power plants since the varying water pressure may increase or decrease the speed. The governor operates the water nozzle. They were also used in speed control of mechanical music box earlier. That's all. Thank you.